Dr. King, and today I'm going to give you a quick tutorial on NMR, and specifically carbon-13 NMR, to help you navigate your lab this coming week. So here's the start. I'll talk a little bit about how the instrument works, a little bit of theory for a few minutes, and then we'll very practically look at a couple molecules and see what their spectra would look like, and hopefully that will be plenty to help the lab go smoothly. So first of all, let me describe NMR is a type of spectroscopy. So it's in the category or family of instruments that are using electromagnetic radiation and interacting that with material. So as a little bit of a refresher, maybe from first semester, UV and visible light has enough energy to excite electrons. So visible light can excite electrons. We see that perceived as colors. UV light can have enough energy to actually eject or ionize, knock electrons off of molecules, and that's the damage that can be caused by UV radiation. But if we move the other direction, which is where we're going here, the energy goes down. And so if we move out of the red, visible, and the red end of the spectrum, we get to infrared light, and infrared light has enough energy not to really promote electrons, but to cause electrons involved in bonds to vibrate. So we think of that as heat energy. We go further, we get to microwaves, and eventually we get into the radio frequency range of the spectrum, and that is the part of the spectrum that NMR takes advantage of. NMR uses radio frequency radiation to cause the nuclei. So I'll pause here for a second, because all of chemistry, we're talking about valence electrons, right? But if we're talking about nuclear chemistry, radioactivity, and in the context of NMR, we're actually talking about the nucleus. So I mean the nucleus when I say nucleus and not the atom. But radio frequency radiation has enough energy to cause nuclei, which are spinning, to change their spin orientation. And we'll talk briefly about how that works. Alright, so your nuclei, if you have an odd number of protons and neutrons, or protons or neutrons, if you have an odd number of them, then these nuclei tend to be really sensitive to radio frequency radiation. So carbon, most carbon, 99% of carbon atoms are carbon-12, have the isotope 12, mass of 12, has 6 protons and 6 neutrons. Those are both even numbers, so carbon-12 is not very sensitive at all in the NMR. But carbon-13, the carbon-13 isotope, is actually quite sensitive because of those odd number of neutrons. So about 1% of carbons are carbon-13s. So there's enough of them present in organic molecules for us to do this analysis. We can use NMR to study other nuclei. NMR is the instrumentation that evolved eventually into the MRI, so it uses imaging for health reasons. And in those instruments, they're looking at hydrogen atoms and not carbon-13s. But basically what you'll see when you come to the lab is a fairly big magnet with a small hole. You have a small tube with our sample in it that we'll go into. And if you were to go to an MRI lab, you'd see an enormous magnet with a big hole that you put a person inside. And there's some sophistication, some added bells and whistles to make the MRI produce images, but the root technology is the same. Alright, so here's what's happening in the instrument when we put our sample inside this instrument. There's two big players, but the most important factor is there's a large magnet. So your nuclei, particularly ones that have these odd numbers of neutrons or protons, they are spinning, and they have an electromagnetic field. So all charged particles that are rotating have their own electromagnetic fields, and they do affect each other. So I don't want to say it's completely random, but if you could somehow look at all your nuclei, they're basically all going to be spinning in opposite directions. They're influencing each other, but it's going to be kind of a jumbled mess. However, if you put yourself or a solution of material inside a very strong magnetic field, it'll force those nuclei to all line up with that external magnetic field. And so now, instead of all your nuclei doing some basically random motions, they're actually now all pretty much aligned and ordered and organized. So inside a magnetic field, the nuclei want to line up with it, and that's what we will consider the ground state. So that's where the nuclei want to be. So inside a magnetic field, while the molecules are there, if you could shine infrared radio frequency radiation at the material, there would be a specific frequency with a cause in each one of those nuclei to flip their spin orientation against the magnetic field, and that they don't want to be there. That's essentially the excited state. Then if we turn off the radio frequency radiation, those nuclei will all relax. They'll all flip back to align with the magnetic field, and when they do that, they're going to emit that energy. They have to get rid of that energy. They're going to emit that in the form of radio frequency radiation. So the way the sort of modern NMRs work is essentially an emission instrument. So we use broad RF signals to excite all of the nuclei against the magnet, and then the RF signal stops, and as the nuclei relax, they're going to emit radio frequency, and we, the instrument, is actually going to record what frequencies are being emitted by the sample. And that's kind of how the data is generated. But to make sense of the type of spectra, and we'll draw a few here in a moment, is that the energy that it takes to excite a nuclei against the magnetic field, and correspondingly the energy you get emitted when they relax, those are the same values, those are dependent on the magnetic field strength. Okay? But we're using the same magnet for every molecule and every atom in the molecules. So where we learn something about what this molecule looks like is that within the molecule they all have their own subtly different electromagnetic environments. So for example, if we look at this first molecule here of 3-carbon chain, this is propane, the carbon on the end, let's say, we'll call this carbon number 1. Carbon number 1, it actually doesn't feel the full strength of the external magnet that it's in, because look around that carbon. That carbon nuclei has its own electron density around it. Those are electrons, they're spinning, they have their own electromagnetic fields. And the hydrogen atoms, they all have nuclei that are around this carbon. There's an adjacent carbon. So there's a lot of atoms and particles around this nuclei. They all have their electromagnetic fields. And what explains sort of all the behavior here is this one idea, that the other electromagnetic fields, so electron density, so the electron clouds that are around these nuclei, they effectively shield the nuclei from feeling the full force of the external magnet. And it's sort of a blanket, and they provide the term we use is shielding. And that being the case, the scale, you'll see on this axis 0 to 200, it's not quite an arbitrary scale, but it's designed such that 0, so at this end of the scale, would be the resonant energy for a normal carbon. So, what's normal, and that's somewhat debatable, but if we have a carbon, let's say something like methane, let's just make it as simple as possible. These bonds, the carbon-hydrogen bonds, are fairly nonpolar, and so the electron density around the carbon is maybe what we would say is fairly normal. And so this we would expect to have a frequency that would land it down at this end of the spectrum. The right end of the spectrum we would call, so we refer to as being upfield shifted. Now, as we add other other groups. So imagine an oxygen and then a hydrogen. So make this methanol. That oxygen, you know, is very electronegative, and so it pulls electron density away from the carbon. And so you have your carbon nuclei, the oxygen here is pulling electron density away. It actually exposes that carbon nucleus to more of the external magnetic field, which means it takes more energy to flip it against the magnet, but more importantly, when it relaxes, it gives off RF radiation at a higher energy. And that ends up being downfield. So this end is high energy, this end of the field is low energy. And you could also associate this with normal. And this end of the spectrum, things will shift down here because of electronegative groups, so oxygens and chlorines and nitrogens, double bonds, aromatic rings, and then actual branching. So down here we'll see things upfield if they're on the end of the chain, so terminal groups, or if they're internal, they'll tend to be more downfield. Alright, so that's kind of the overview. So let's, I'll kind of summarize this basically as we work through a couple examples. So here we have this molecule propane, and the carbons are fairly similar in chemistry. There's no electronegative groups. There's no double bonds, nothing really unusual. And so the only difference here is we have carbons that are on the end, and once again, if you compare it to methane, it's probably most like that, right? So these terminal carbons are going to be the most upfield. So I'm going to see a signal, let's say somewhere over here. Now if you compare carbon number 1 with carbon number 3, hopefully you'd see, because of symmetry, they are identical. So they're both going to emit the same frequency, which means that this peak I should expect to be twice as big. This carbon here in the middle, it's not very electronegative, there's nothing very unusual here, it's just internal, so it's not going to be very far downfield, but I'm going to probably see a peak that should be to the left of our terminal carbon group, and this is pretty much what the spectrum should look like for propane. We have two peaks. I know that this one is probably terminal, this one is internal, and I see the ratios of about 2 to 1. So this accounts for my two terminal CH3 groups and the internal CH2. Alright, so we would expect it to look like this. Alright, so let's make it a little more unusual. Let's replace the a hydrogen on the center carbon with an alcohol group here, and that is going to cause things to move downfield. So the carbon that's right on, so we'll say, I'll start with carbon number 2. So it has the alcohol on it. It's definitely withdrawing electron density away. That's going to get exposed to the external magnetic field. We're going to have more energy associated with it, and we'll probably see a peak that's downfield. And yeah, this looks like a typo here. In carbon, our scale will be about 0 to about 200, so I'm calling that 100 here. So I'm going to see a peak, but you'll see that this thing is shifted, the center carbon. It's the same carbon that's generating these signals, but it's much further downfield here in this case because of the oxygen. Alright, then our carbon number 1 and carbon number 3, they are still identical, so they're going to give me a signal that's twice as big, and they'll be more upfield than this other one. And if I had to guess, it's probably going to be somewhere like this. And if I compare these two, they should be the same height, they're the same abundance, but it should be a little bit, this one should be a little bit downfield than as compared to the one in propane, because although the oxygen's not on it, the oxygen is a couple atoms away, it still is withdrawing electron density from that whole molecule towards itself. So this spectrum here is what I'd expect to see, something like this for 2-propanol. And in case the common name is isopropanol, this is rubbing alcohol that you would maybe have in your medicine cabinet. All right, so I just have one more. We'll kind of just round this up. So a little bigger molecule. It's certainly not very complicated, but we see symmetry. This is pentane. So we have 1, 2, 3, 4, and 5 carbons. We should see that the 1 and the 5 carbon are the same, 2 and the 4 are the same, and 3 is unique. And so like before, these terminal carbons will be downfield here. I think numerically, they're going to be something like 10 parts per million. And so this is what will allow you, when you see in the spectra where they show up, you can go to those shift charts that are available to you in the lab, and you can actually make some maybe predictions as to what characteristics or what functional group, what atoms would cause a carbon to resonate at this energy as opposed to another. But these rather boring, we'll say hydrocarbon terminal carbons, will resonate somewhere around 10. And then as we move internal, so carbon number 2 and carbon number 4, they are identical. As we move further inside, it's going to move downfield, and so we'll have another peak. But because it's still represented by 2 carbons, it'll be just as abundant. And then carbon number 3 is most internal, furthest from the edge, and so it's going to be the most downfield. And there's only one of these, so this peak should be a little bit smaller. All right, so this is the idea. Clearly this is meant to be just as an introduction, so that in lab you can pretty well jump right into some practice and fine-tuning your understanding here. But if I were to summarize, so pentane, use this molecule as an example. We have a solution of pentane. It goes into the magnet, it goes into the instrument, and you'll get a chance to do this. So it gets loaded into the instrument, it feels this big magnetic field, and so all these nuclei are essentially going to spin and align themselves together to line themselves up with the magnetic field. Then we pulse RF radiation at the sample, and it causes all these nuclei to flip their orientation, so now they're spinning against the external magnet, and then when we turn off that pulse of RF radiation, they're all going to relax, and when they relax, they emit RF radiation, and when we measure what's emitted, this spectrum down here that we just drew, this is what we get. And the fact that there is signal, that's meaningful, right? We see 3 signals, but they have meaning in a sense that, in light of what we also don't see. So the fact we don't see emission anywhere here tells us that there are things that are not present. We know there aren't carbonyls, there aren't aromatic rings. So we basically focus obviously on the peaks, but essentially when we excite pentane and it relaxes, it's going to emit 3 frequencies. And if we can measure what those frequencies are, so they're energies, that's the x-axis information, and how much of it, that's the y-axis information, it can give us a pretty good idea of what the molecules are. Now, also maybe as a teaser, is carbon-13 is only one of many experiments we can run with an NMR. We could also analyze the hydrogens that are present. If there are nitrogens, you can look at those, and chlorines and fluorine, so we can look at other elements as well and get a better picture. But we can do pretty well in your lab today just by looking at the carbons and making sense of it. So anyhow, I hope this is clear and helps you get a good start in lab this week. And your chance to work with NMR, particularly in a freshman class, this is an unusual thing. So excited you get a chance to do it. Many of you will move on to organic chemistry next year, in which case NMR becomes a regular tool for you, because in that class you're making these organic compounds and you're going to go and use the NMR to analyze and see if you made what you were trying to make, things like that. So this is part of that development. So anyhow, thanks for listening. It's nice to share with you a little bit, and I hope you have a great week.